Good morning, students. Now in this class we will see scattering of particles, angle of scattering and Rutherford scattering. In the last lecture I taught about Kepler's laws of planetary motion, how the second law of Kepler is proved with the help of Lagrangian equations. Then we have derived first integral equation of motion in a central force field, then expression for T and expression for theta. Then we will calculate the differential orbital equation. Here, now we will see what is scattering of particles. We heard this term scattering of particles in optics. Similarly, we heard Compton scattering. Then in diffraction also we will find out the word scattering of particles. Here also in the central force field, this scattering of particles is used to find out the path adopted by a particle. Basically, the path adopted by a particle in a motion under central force field gives the information about the dependence of potential energy on the radial distance r. In the earlier lecture, we saw this equation of mr dot square plus L square by 2 mr square plus V of r, that is equal to 0. Here this half mr dot square plus L square by 2 mr square is the kinetic energy term, and V of r is the potential energy term, that is equal to E, that is the total energy is equal to the summation of potential energy plus kinetic energy, which is nothing but the conservation of energy, which is proved in the earlier lecture in first integral equation. So from that equation, V of r is equal to E minus L square by 2 mr square minus r mr dot square. Now here substitute u is equal to 1 by r. Therefore this term becomes V of 1 by u, that is equal to E minus L square by 2 mr square minus r mr dot square. Similarly, we already know dr by dt, that is equal to minus L by m du by d theta. Substitute here r dot square, instead of r dot, the dr by dt is nothing but r dot, therefore square this term minus L square by m L square by 2m square du by d theta into m will be cancelled, so the remaining term is L square by 2m du by d theta the whole square. Just solve it. If you have any doubt, please ask. Therefore this equation becomes V of 1 by u, that is equal to E minus L square by 2m into u square minus L square by 2m du by d theta the whole square. This above equation clearly shows that the potential energy is dependent on r. The potential energy is purely depends upon r. But for atomic particles, it is not always possible to observe the path of the orbit. For atomic particles, it is not always possible to observe the path of the orbit. And also, this dependence of potential energy on r with the help of orbit equation. We already solved the orbit equation in the earlier lecture. Using that orbit equation, we can't exactly predict the dependence of potential energy on r. So a new method was introduced in order to find out the path adopted by the particle in a central force field, which is called as method of scattering. So this method of scattering is employed to find the potential energy dependence on r. Okay, right. What is basically takes place, or what basically happens in the scattering? Let us consider a particle and consider another particle. The first particle will hit or will apply a force on the another particle. And what happens? the deflection of the first particle is measured. The deflection of the first particle is measured. That is, when this collision takes place, it will be scattered in one direction. It will be scattered in one direction. So that deflection of the first particle is measured. This particle will not follow unbounded orbit. Will follow the unbounded orbit, because it will be deflected depends upon the force that what we are giving. Therefore, we don't know what is the exact orbit position. So this particle will follow unbounded orbit. As the particle is at infinite distance from the center of the force, as this particle is at infinite distance from the center of the force, the particle starts the journey in a straight line. Let us consider if this particle is coming here and it is coming from infinite distance, and it comes here in a straight line path and it hits the particle. It hits the particle and it begins to deflect from its straight line path as it approaches the center. Okay, consider here the particle is there. In order to explain the path, you consider from here. For example, from here, the particle is moving and it is approaching in a straight line. As it approaches the center, it again deflects back in this direction. So the particle starts here, moves in a straight line. As it approaches the center, it will be deflected in the another way. As the time goes on, it moves away from the center and finally it reaches again the straight line trajectory. What happens in general? Final direction of motion, this is the motion of the final direction. Final direction of the motion is not same as the initial direction. Is not as the initial direction. This phenomenon is called scattering. This phenomenon is called scattering. That is, the first particle is scattered. The first particle is scattered, or said to be scattered. Now, the angle between the initial and scattered direction is called angle of scattering. The angle between the initial and scattered direction is called angle of scattering, and it is denoted by the letter this. That is, make a 0, and inside that 0 you make a AC symbol. We know this AC symbol well like this. AC symbol will be, you will write the AC symbol like this, na? You make it right. So this is the theta. Otherwise, now I will use the term theta here, but the symbolic representation is like this. Okay, right. So what will be this value? This theta value. This theta that should be is equal to pi minus 2 pi naught. Pi minus 2 pi naught. What is the value of pi naught? This is the value of pi naught. That is, pi naught is the angle which the initial and the final radius vectors from the center of force makes with the symmetry axis. So this is the symmetry axis. Then this initial and final vectors, radial vectors, initial motion and final motion radius vector angle is called as pi naught. So this theta value should be is equal to pi minus 2 pi naught. 2 pi naught. Okay? Okay. Now we will find out what is the expression for angle of scattering. We know that angle of scattering is nothing but the angle between the initial and the scattered directions. Now let us consider the initial velocity of the particle is v0. Initial velocity of the particle is v0. Consider the particle is traveling undeflected from here. If this image is in the next slide, it will be big in size. Now I just for the explanation I here make this in a smaller size. So a particle coming from this area, it is undeflected and it will be passing, that means it hits. It basically, what here this image is representing is, it is the cross-sectional area. So when a particle hits on another particle, a scattering will be takes place. That scattering area will be like this. The scattering area will be like this. Okay. So now you see. Consider a particle is traveling undeflected and pass a distance s and pass a distance s from the center of the force. The distance is defined as the perpendicular distance between the center of the force and the incident velocity. The perpendicular distance between the center of the force and the incident velocity is called the distance s. It is otherwise called as impact parameter. It is otherwise called as impact parameter. Now calculate the energy and angular momentum in terms of speed and impact parameter. So what is the formula? Is equal to half m v naught square. But we know that v naught square is nothing but 2e by m, or v naught is equal to root 2e by m. Substitute this value here. This is the energy term. This is the angular momentum term. Angular momentum formula is L is equal to m v naught into s. Therefore L is equal to m, instead of v naught, substitute this value root 2e by root m into s, or L is equal to s into root of 2m. From this figure, it is clear that tan theta by 2, that is equal to cot pi naught. Tan theta by 2 is equal to cot pi naught. But cot pi naught, that is equal to epsilon square minus 1 whole power minus half. Cot pi naught is equal to epsilon square minus 1 whole power minus half, where this epsilon is called eccentricity of the orbit. This epsilon is called eccentricity of the orbit. What will be the value of epsilon? Epsilon is equal to 1 plus 2e l square by mk square whole power half. Epsilon is equal to 1 plus 2e l square divided by mk square whole power half. These equations, this epsilon value, this cot pi naught value, all will taken from the Kepler's laws of motion. All taken from Kepler's laws of motion, but it is not in your syllabus, so I have taken only the formula here. You just take this formula and write the equation. Okay, epsilon is equal to 1 plus 2e l square divided by mk square whole power half. Depends upon the eccentricity only what will be the shape of the orbit. We may calculate what will be the shape of the orbit if epsilon greater than 1, if epsilon less than 1, if epsilon is equal to 0. So for each value, whether it is elliptical orbit or it is a circular orbit or it is a parabola, like that. So it depends. The value of eccentricity explains the structure of the orbit. So it is not in your syllabus, so that's why I just used this formula, epsilon that is equal to 1 plus 2e l square divided by mk square whole power half. The total cross-sectional area. What will be the total cross-sectional area? It is the integration of sigma theta pi over the subtended angle 4 pi. Total cross-sectional area is the integration of sigma theta pi, that is the sigma, that total cross-sectional area is the function of theta and pi, or the subtended angle 4 pi, or the subtended angle 4 pi. Therefore this equation becomes sigma t, that is equal to integral 4 pi sigma pi comma theta d pi. For a central force field, the distribution of the particle will not depend upon pi, because there must be complete symmetry around the axis of incident beam. That is, as the symmetry around the axis of the incident beam is complete, the value of pi will not appear, so it mainly depends upon theta. Hence, the distribution of the scattered particle should be same within the ring area. Therefore, within the ring area, you see this ring is like a circle. Okay, this ring is looking like a circle. Therefore, what will be the formula? 2 pi r square sin theta d theta. The solid angle subtended by this ring area on the scattering center, which will be equal to this term will be divided by r square. Therefore, 2 pi r square sin theta d theta divided by r square. This r square will be cancelled. The remaining term will be 2 pi sin theta d theta, which is nothing but the solid subtended by the ring area on the scattered center. The number of particles scattered, through the solid angle should be per unit time should be, that is solid angle will be 2 pi sin theta d theta, then multiply it with I into sigma theta. Therefore, the number of particles scattered through a solid angle 2 pi sin theta d theta will be I into sigma of theta into 2 pi sin theta d theta. Let it be equation number 2. The number of particles scattered into the solid angle lying between theta and theta plus d theta must be equal to the number of particles passing through the ring of radius s with the width ds. You refer the earlier diagram. S and ds. The number of particles scattered into the solid angle lying between theta and theta plus d theta must be equal to the number of particles scattered through a solid angle of radius s and with ds. Therefore, the value should be I into 2 pi s into ds. I into 2 pi s into ds. Now, equate these 2 and 3 equation, you will get theta sigma of theta. This is the differential cross-sectional area or angle of the scattering. Sigma theta, that should be is equal to minus s divided by sin theta ds by d theta. This negative sign implies that theta decreases as s increases. Theta decreases as s increases. This is the main physical part. The larger the impact factor, the smaller will be the angle through which the particles will be scattered. So, if the impact parameter value is higher, the angle through which the particle will be scattered will be small. The differential cross-section area is a measure of the probability that the particle will be scattered through a solid angle d omega along the direction theta and pi. Therefore, the differential cross-section is a measure of the probability that a particle will be scattered through a solid angle d omega along the direction theta and pi. So, this is the expression for angle of scattering or differential cross-sectional area. Okay. Now we will see what is Rutherford scattering. We already heard the term Rutherford scattering in atomic physics. That is Rutherford scattering of gold atom. Rutherford scattering of gold atom. You might study in atomic physics. Here I am taking this Rutherford scattering of a charged particle by Coulomb's law. We know Coulomb's law. That is, the force of attraction is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Now let us consider Ze. Ze is the atomic number, E is the charge. Ze is the charge at a fixed center of force which repels the incident particles having a charge of Z dash E. There are two particles. One has the charge ZE and another one is Z dash E. Therefore, the force between them will be F is equal to Z dash E square divided by R square, or F is equal to minus K by R square, where K is equal to minus Z dash E square. From this equation, we will find out what will be the shape of the orbit. So when a scattering taking place, shape of the orbit will come. So we already know the equation in the earlier slides. 1 by R is equal to mk by L square 1 plus epsilon cos theta. From where it comes, 1 by R is equal to mk by L square 1 plus 2EL square by mk square whole power of cos theta, where this epsilon is called as eccentricity. Already in the last slide I told about this eccentricity, which represents a conic section. This the structure will be a conic structure for F is equal to minus K by R square. Now, in this equation, that is 1 by R equal to mk by L square 1 plus 2EL square by mk square half cos theta, substitute the value of K here. Therefore, 1 by R is equal to, substitute this value, what will happen? Minus Z dash E square by E square M by L square into this whole bracket term will come. Since epsilon is equal to, we know 1 plus 2EL square M into Z dash by E square by 2 is greater than 1. I already told, depends upon the eccentricity, the shape of the orbit will change. This value will be greater than 1. When this value is greater than 1, what happens? When this value is greater than 1, the cross-sectional area will be, or the conic section area, not cross-section area, this conic section is a hyperbola. Therefore, the structure will be hyperbola. In the next slide, I will show that hyperbola structure. So, the conic section is a hyperbola. From this, we can find out the shape of the orbit. Then, what is the differential cross section? We already calculated the formula, differential cross section formula. You see here, sigma of S is equal, sigma of theta is equal to minus S by sin theta ds by d theta. So, what will be the differential cross sectional area for this Rutherford scattering? We know that tan theta by 2, that should be equal to K divided by 2SE. Substitute the value of K here, minus Z dash E square divided by 2S into E, or S is equal to minus Z dash E square by 2E cot pi by 2. Theta by 2. Cot theta by 2. Differentiate this equation, ds by d theta, that should be equal to minus Z dash E square by 2E 1 by 2 cot theta. When differentiating, you will get cosecant square theta by 2. Now, we know the value of S and ds by d theta. Therefore, differential cross-sectional area should be equal to theta, sigma of theta, that should be equal to minus S by sin theta ds by d theta. Substitute the value of S and ds by d theta here. And you will get the value, differential cross-sectional area, sigma of theta should be equal to 1 by 4 Z dash E square by 2E the whole square 1 by sin power 4 theta by 2. By applying this value and cross multiplying and solving, we will get this value. This is called Rutherford scattering equation. This is called Rutherford equation. So what this equation implies? From this equation, what are the inference we are finding? That is our inferences. What this equation implies. This cross section is strongly depend on the velocity of the incoming particle and the scattering angle. So the scattering angle and velocity of the particle are responsible for this cross sectional area. Also, this cross-sectional area increases rapidly with increasing charge. Increasing rapidly with increasing charge. That is, it is a multiplication of z dash e square. Therefore, as the charge increases, cross-sectional area also increases as it is directly proportional. Similarly, z is nothing but the atomic number. Therefore, as the atomic number increases, then this scattering cross section also increases. So this is the first point. Then, in order to investigate the structure of the atom at small distances, high velocity particles will be used, for which the distance of closest approach is small. As we already told, as the distance is small, scattering is more. Therefore, high energy particle, high energy or high velocity particles means the distance of closest approach will be small. Therefore, we will get the scattering angle very easily, and also we will easily find out the structure of the atom for small distances. The cross section is large for small values of the scattering angle. We already know these things. The cross section is large for small values of the scattering angle. This is the hyperbola structure. You see, this is the hyperbola structure. That is, as the conical value increases, the eccentricity value will be greater than 1. That is, eccentricity is equal to C divided by A, where A is the semi-major axis and C is the linear eccentricity. Therefore, as the eccentricity is greater than 1, it represents the structure will be a hyperbola structure. Hence, we get in Rutherford scattering hyperbola structure. So, this is Rutherford scattering. I think it may be difficult to understand this Rutherford scattering and scattering cross section. So you read again and again, then you will easily understand the things. If you have any doubt, you please ask me in the class or in Google Classroom, then I will reply you. Okay, so in this lecture, what we saw about scattering angle of scattering, differential cross-sectional area, how we can calculate the differential cross-sectional area, then what is Rutherford scattering. I think that this scattering is somewhat difficult to understand, so you read more and more and you will get the clear picture. In the question paper they are asking this scattering question regularly, therefore you please read, and if you have any doubt you ask me anytime, I will clarify. Okay, have a nice day.